So processes that we're interested in are often expressed in the form of a differential equation. Here's an example. This is an equation for a concentration as a function of distance, and it's a first order ordinary differential equation. What it says is the gradient of concentration is proportional to a constant minus the concentration itself. So when the concentration is equal to 0, the gradient is equal to A. And then as the concentration increases, the gradient becomes increasingly negative. So that's what this equation says. It says really how the concentration is changing in space. And the second equation tells us what the concentration is at x equals 0. It equals this constant value, C sub b. So this is information about the concentration, how it changes in space, and what it equals at a particular location. What we want to do then is to solve this equation so we can get an equation that gives us concentration distributed along x. And that's possible to do by solving this differential equation solving this differential equation here with this secondary equation as a boundary condition. So to do this in Scientific Notebook, we have a couple of options. The first one we'll try is to enter the equation in a matrix like this. This is just to get things organized, and what we're doing is essentially saying that we have two equations that we want to satisfy at the same time, those two equations. And so Scientific Notebook has a built-in capability to solve ordinary differential equations. And if we go to commute and come down here to solve ODE, and we'll use the exact solution method, and this is the result. So this is a closed form expression in that it's an equation that is solvable by just plugging in some variables. The thing that's implied here is that this stuff here that I'm going to just copy and paste down here is equal to C. So the dependent variable, this guy C, is equal to this solution here. So this is the result, but it's kind of awkward. It's kind of big and clunky. We have an exponential here and then logarithm up in the exponential. So the first thing we'll do is see if this can be simplified by Scientific Notebook. So we highlight that and go to Simplify, select that. And so we see that indeed it can be simplified somewhat. This exponential with a log up here can be simplified down, and we have this result. This can be simplified a bit more, and the way I'm going to do it is to copy and paste, and I'll do it in a couple of steps. What's convenient is to factor out A from these two expressions, and then also multiply through by B. So we'll have a ratio of A to B here, and that B will cancel out this B right here. So in Scientific Notebook, it's nice to, it's easy to just copy and paste and duplicate things. So what I'm going to do is use that capability to copy and paste to do the algebra in a few steps. So there I multiplied through by B, and now I'm going to drop these parentheses, and now I'm going to copy and paste again and factor out the A over B. So I put that in parentheses, and then I'm going to take this out, put one there, and I get that result. And what I find is that if I do this in small steps, so going from here to here, I just make just like a single algebra adjustment, that it's pretty easy to follow each one of these steps. I can also go in and write in what I've done, so that makes it even easier. So I go like this: multiply, well, we need to make it into text, so multiply through by b, and this is drop okay, and then we get the final result. And what we need to recognize is that we started up here with C being equal to this stuff, and what we've been doing ever since is really just working with the right hand side. So when we get to the result, we will copy this back down there, and then, well, I guess the easiest thing to do is just go like this: C equals there, and that's the final result. Okay, so let me show you now a different way to do this. This method right here used the ability of Scientific Notebook to solve ordinary differential equations. We don't really see how it did it, and so this is okay for some applications, but one of the problems is that if Scientific Notebook can't solve it, then you're out of luck. And in some cases, as we'll see, Scientific Notebook can't solve the equation, and we can solve it though using separation of variables ourselves. And if this is the case, then this separation of variables method, this is often in our class what we'll use when we solve these equations by hand. And so Scientific Notebook offers the ability to check this method, and in some cases, as we'll see, it can't solve the equation using the built-in ODE solver, but we can still do it using separation of variables. So here's the way this is going to work. We have this equation here, this ordinary differential equation. Separation of variables will allow us to solve this equation if we can get all of the dependent variables on one side and independent variables on the other side. So in this case, C is the dependent variable, that's what we're solving for, and X is the independent variable. So we can separate this equation like this. I'm just going to take all of that stuff and bring it over on this side, and the dx we multiply through by, and we get that. So this is the same equation, we've just rearranged the terms, and in this case all the c's, everything's over on this side, except there are no terms that are with respect to x over here, and then the dx is over on this side. So this equation is now separated, and what we can do is integrate both sides. So we put in this integration, put in the integration there, and get the result. Now in this form we can't really get Scientific Notebook to give us a good outcome, so what we'll do is just solve each one of these sides of the equation independently. So we'll first do this integral, and we just set it up like that and use evaluate, and there's the result. And then we'll also solve this right hand side, and this is really just trivial, but we'll solve it anyway. So the integral of dx is just equal to x. So now we're going to take this result here and substitute it. Basically, we're just equating these two results. Okay, so this equation here, once we integrate it, we get this. But we have to also recognize that when we do this integral here, this is an indefinite integral, so it produces a constant of integration. Like so. So that's the result of the integration. Now, what we did up here was we had two equations. We had the differential equation and we had the boundary condition. So the boundary condition is really essentially another equation that we have. It's additional information about the problem that we have to use to solve it. And so up until this point we haven't used the boundary condition, but we'll use it now to solve for the constant. Okay, so we need to figure out what that is. Well, what this says is that C equals C sub b at x equals 0. So the way we can use this information in the result that we just obtained is to take this result here and substitute in the initial condition. So I can substitute by using these square brackets, and then if I write it like this, C equals CB and x equals 0. So I make CB a subscript, and then I make all of this stuff here a subscript. Now, this is the format that Scientific Notebook uses for substitution. It's going to take these two expressions and substitute it into this stuff here. So when I do that, I'm going to hit evaluate here, and here's the result. That's the constant that I get when I make this substitution, and this substitution right here is the boundary condition. Okay, so that's the procedure for solving for the constant. And now what we need to do to complete this analysis is to take this expression for the constant that I'll put down here and substitute it back into the equation here. So I'm gonna copy this down, and this will be, let me put it here. Just put in some notes here. This is the constant of integration, and this is the result from integrating ODE. So then we will substitute, and we'll get this. So that's the result, and I'm just going to take this and put it in here. Cut and paste. So that is the result then, and we have concentration here as a function of x and constants. So this is the result. It's a little bit awkward though, form, and so what we want to do is have concentration on the left side and functions of x on the right side, and so we'll do some algebra to get there. So I'm going to copy and paste, and what I'll do first is take this stuff and put it over here on this side. So the sign changes like that. So there's step 1. And step 2, I'm going to multiply through by minus b. So there's 1 over b, so if I multiply through by minus b, that just becomes minus, and that becomes plus. And now I have this, I have 2 log terms here that can be combined. So I'm going to copy and paste again, and if I have log of this stuff minus log of that stuff, then this will just become log of that stuff divided by log of this stuff. Okay, so that's the next step, and then I'm going to copy and paste again, and see this has this minus 1 over b here and minus 1 over b there, so those cancel. And let's copy and paste it again. Okay, so now what I think we need to do is raise e to both sides. So e to this side and e to the log of this stuff, we'll just get rid of the log. So we get that. And copy and paste it, and now multiply through by AB. What I'm trying to do here is, there is a method to this madness. What I'm trying to do is get this guy, this C, over on the left hand side. Okay, so if I go back up here, there it is. That should be on the left hand side, and the X should be on the right hand side. So all of this gyration here has been motivated by trying to do that. So I've got this all constants and X, so I'm heading in the right direction. I got to get that isolated, so let's copy and paste it again, and this is just going to be simplified by that. And now I'll add a to both sides. No, subtract a from both sides. And I'm going to divide through by minus b. Okay, so that's going to be 1 over b, and that's plus. So minus b, that'll be plus, and that's minus a over b. Okay, so there are a lot of steps here, but each step is a small one, and we should be able to go and just recognize what the step is. Like we did up here, we can also go and put in the notes, and I'd recommend that you do that. I'm not going to take the time to do that here because hopefully you followed it, and we won't really need to write it out here. But I would recommend that you do it so that somebody looking at your notes, like me or like you down the road, can recognize it without ambiguity. So we're just about done, but in fact, we've achieved the result we want. We have concentration over on this side and X over on this side. What we can do though is just adjust this a little bit more, and I think if we do that, we'll come up with a result that makes it a little more insightful. So what I'm going to do is multiply through by this term. Okay, so that's just this multiplied out, and then I can factor out a over b from the first and the last term. And there's the result. If we then take this result here and compare it to what we did up here from the solution that Scientific Notebook gave us directly, we see that they're indeed the same. Okay, took us a bit longer, some more steps with separation of variables, but nevertheless we get the same result. This result is interesting because we can understand what's happening with the concentration. This part of it says the concentration is increasing and approaching a value that's equal to A over B, and this part of it says the concentration is decaying to 0. It's starting at CB and decaying to 0. So presumably the values of A and B and the terms that are in there can be used to, when we substitute in, we can use that to get some insights into the problem. And indeed, we'll do that as we go through and solve problems like this one. Now, what I'd like to do before we leave this problem is to show you that we can check and see whether this is indeed the right result. So if we check this, the procedure is like so. We start with this, well, really with these two equations. These are what we say characterize our problem. So the result we now say is this. And so the check is, does this equation satisfy these two equations? So what we do is substitute in and see. So the first thing, the easiest one, is just to see if it satisfies this this boundary condition. So here's how we can do that. So the concentration equals this, and if we go and substitute in x equals 0, we should get that the concentration equals C sub B. And indeed we do. And it's easy to see. When x equals 0, that equals 1, and that cancels. That's all just equal to 0. And this equals 1, and we get C sub B. So that checks. And now we need to check this side. And so the way to do that is to say, well, I'm going to take this value or this expression for C. And what this equation says is that the derivative of C with respect to x has to equal A minus B times C. So I'm going to take this expression for C, and I'm going to substitute into these two sides. So let's see. That is going to equal the derivative of this expression. So we'll just go like this. And solve that. And there's the result. And now what we do for the other side is we take this side here and substitute in C. Well, we can just go and copy this. Substitute that in. And that equals that stuff. And we have to simplify. Let's try this. Okay. So that simplifies down to this result. So this is the derivative. We work it through and we get that. And that's this side. This side we substitute in and we get that expression. They are equal, and so we essentially are checking the solution. This expression for concentration satisfies that equation there. So in addition to this video, there are also some notes that are written out in more detail in Scientific Notebook. So check out that file. It's a supplement that's also posted in Blackboard.